All right, kids, we're going to revisit section 3, and we're going to talk about the two things that we skipped over before. One is rationalizing to evaluate a limit, and the second is using the squeeze theorem. So when we're rationalizing, we really could have learned this before, but given the nature of our pace, it would have been a lot to do in 50 minutes. So another way to find a limit analytically is rationalizing, right? We could, if possible, factor out and cancel things, right? When we get that indeterminate form, that 0 over 0, when we try to evaluate, we know that we can simplify somehow. And that ability to simplify is going to be important for rationalizing also. If we see that we get that indeterminate form, that gives us a clue that we could probably do something else. All right, so like if we're trying to evaluate this limit, right? If I plug in 0, I get 0 plus 1 is 1, square root of 1 is 1, 1 minus 1, 0. If I plug in 0 in the denominator, 0. 0 over 0 tells me, oh, something can happen. We could do something here. And what we're going to do is rationalize, or in general, we're going to multiply by the conjugate. We need to simplify the numerator actually, so that what happens is that we're creating a term that's going to cause the whole fraction not to be indeterminate when we evaluate. So when we do this, we're going to multiply by the conjugate. Okay, the conjugate is just, this is like the difference of squares. Here we have minus, so we're changing it to plus, and we're multiplying by the two terms with the opposite sign. So if this would have been plus, we would have done minus instead, but this is what we're dealing with. Okay, so we're multiplying by this conjugate in the numerator and the denominator. This is the ugliest one that you've ever seen, right? These cancel. We're not changing the value of the fraction. We're just changing how it looks. Okay, and in this case, with purpose, so that when we plug in 0, bad things don't happen. So we're going to distribute. And when we multiply the first terms together, what's in the square root just comes out, right? It's this squared. So we get x plus 1. And then I'm going to have one of these and then minus one of these. So the middle terms go away, which is the whole difference of squares thing, which is why we're picking the conjugate. And then we'll have minus 1 squared. Okay, in the denominator, we're just kind of distributing, but we don't need to distribute it just yet. Don't go crazy and try to simplify just yet. When I simplify plus 1 minus 1, now I have x and x in the denominator, and those x's can simplify. So we didn't want to multiply this through because I'm going to end up canceling it anyway. Whenever we cancel everything from the numerator, we're left with just 1. That's a factor of 1. And now if I plug in 0, if I take the limit as x approaches 0, in the denominator I have 2. That's okay. This is a half. And if we would have looked at the graph for this original function, we would have seen that it's approaching a half. But it's a lot easier to do that now. Okay? So we rationalized to break up that indeterminate form. And again, looking at the graph, we would have seen that it was actually approaching a half anyway on the left and the right. We can also look at the table and see the same thing. So rationalizing, we're going to practice that here in a little bit, but rationalizing is an important skill to be able to break up the indeterminate form. Okay. Last thing that we're going to talk about is the squeeze theorem. Now, this is more advanced than we need it to be, but I don't want to get through this chapter without at least talking to you about what the squeeze theorem is. As an introductory calculus student, you'll be told more information about this, so you're not having to make all the decisions that would go around the squeeze theorem. But here's the concept, okay? Squeeze theorem concerns the limit of a function that is squeezed between two other functions, okay? Each of which has the same limit at a given x value. So you can see that this function g and the function h and the function f all have the same limit as we're approaching C. Elsewhere, not so much. But what's important is that G is bounding the function. It's above the function everywhere through as we approach the limit. And H is doing the same thing below, right? So we're between. F is between. It's getting squeezed between G and H. So if f of x is between h and g, this is how we're going to read this. F of x is between h and g for all x in the interval containing c, except maybe at c. And if the limit of h, the lower one, is equal to the limit of g, the upper one, then the limit of f exists and is equal to the same limit that these other two are equally. So the squeeze theorem is also called the sandwich theorem or the pinching theorem, and it does the same thing, okay? And we learned these. These are proven through the squeeze theorem. We're not going to take the time to do these two because I told you just need to memorize these and the tangent one that goes along with this. But we're going to talk about another example, okay? So here's our function where we have f in between, right? And we talked about this. We're going to look at this function, okay? Don't know anything about this function. Now, to get the concept, what we would do is, what we can do just to understand how the squeeze theorem is working. This is not normally what we do. We could look at this graphically. So normally we're not looking at the graph. We're actually trying to do the limit analytically. But here's what this function looks like. And this is actually really scaled in, right? This is between negative 0.2 and 0.2. So this is negative 0.2 to 0.2. And we're going up by 0.05, I think. 0.05. And this is one of those functions that it looks like it's going to oscillate a little bit. So we don't know what's going to happen when we get close to zero. If I look at the function, whoa. Sorry, kids. If I look at the function between negative 0.02 and 0.02, look at that oscillation. That's something that we know causes problems with limits. But it seems to be not oscillating as we approach zero. But there's a lot of oscillation here, a lot of oscillation here. It's kind of a cool function, really. Here's my window for this function. Just so you can see, the y values are really, really, really small. I mean, we're almost at the axis here if you look back and we zoom out a little bit. So these y values, this is what's happening as we're really close. And you can't even see that when we're zoomed out. There's a lot of oscillation. If I graph the function x squared and negative x squared, you can see that they sandwich that function as we approach zero. And x squared and negative x squared both, as we approach zero, have a limit of zero. So since this blue function's bounded between the red and this magenta, and both the red and magenta have the limit as x approaches zero that are the same, right? This is that going back to this thing. Both of them approach the same place. Then we can say that the limit of the blue function, this weird thing, approaches zero also. That's graphically, okay? Now, algebraically, analytically, we know that sine of 1 over x has to be between negative 1 and 1. The sine of anything has to be between negative 1 and 1, right? If we're plugging in values, we can't ever take, we're not going to get anything back from sine. If we evaluate sine of something, it's always going to be between negative 1 and 1. But bad things happen when we plug in zero here because we can't evaluate it, which is why we're taking the limit and doing all this fancy stuff, right? So if I multiplied everything in this equation by x squared, that means that negative x squared is between x squared times sine of 1 over x, which was our function, if you remember, which is less than or equal to x squared. My face is in the way. Sorry, kids. But you can see that, okay? So I multiplied I multiplied x squared by everything, and we're algebraically showing that this function has to be between negative x squared and x squared. Okay, that's the analytic approach. We didn't have to look at a graph to know that. That is just from algebra. And we know that the limit of negative x squared and the limit of x squared both approach zero, but is zero as we approach zero. So then the squeeze theorem tells us that the limit of this function that we didn't know anything about must also equal zero. Okay? Generally, when we do squeeze theorem problems, we're given the bounding functions in an introductory calculus class. So you wouldn't have to come up with x squared and negative x squared. As a matter of fact, this is even a little bit advanced for AP calculus. So we're probably not going to do much with this other than here you've been exposed to it. If you go and take calculus in college, if you're going to be in an engineering course or something else, the squeeze theorem is not something you've never heard of before, but we're just trying to squeeze the function we don't know anything about between two functions that we know something about. That's the idea. All right, kids. Really, we're going to work on rationalization. I'm going to put a couple practice problems here in the ed puzzle so we can work on rationalization, and we'll see how you do with that.